Welcome to the deep dive. You came to us with an extremely technical and, frankly, a fascinating source stack this time.
It's a deep one for sure.
We are tracking the architectural evolution of a highly specialized technical framework, a system named Arooka.
And the life cycle here is it's remarkable to follow.
It really is. It begins as this simple declarative vector language embedded right inside an SVG element. And then through this series of really intentional, almost philosophical engineering pivots, it morphs into a full-blown n-dimensional multi-interpreter physics model.
It truly is an exercise in systems thinking. I mean, this isn't just about the finished code. What the sources document so well are those step-by-step engineering decisions.
So why?
Exactly, the architectural necessity that drove every single pivot. We get to see the thought process behind choosing a highly specific language style, managing complex memory structures, and simulating physics deterministically, all within the very real constraints of a browser sandbox.
And that is precisely our mission today. We are going to unpack those design choices, not just to understand the syntax, but to really grasp the philosophical rigor that underpins this entire system.
I think for anyone working in, say, low-level systems, engine design, or even just complex data visualization, it's a masterclass.
It's a shortcut to understanding those foundational principles. What stands out immediately, right from page 1 of the sources, is the core starting principle for this system. The founders called it truth without ornament.
That phrase is the core axiom. It's everything. And it dictates the entire architectural approach from the choice of language right down to how it handles errors.
So what does that mean in practice, truth without ornament?
Well, it demands two things. First, transparent interpretation. And second, a direct, honest mapping from the written code to the visual output.
No magic.
No magic whatsoever. If you write code that attempts to draw something, the system should not perform any hidden parsing, clever state management, or any magical AI-like guesswork to compensate for your input.
So if the input is flawed or impossible, the system has to fail honestly.
It has to.
It has to be inspectable and accountable at every single layer,
Yeah.
right down to the data stack itself.
Precisely. If the system cannot produce an honest result based on the explicit instruction you gave it, it must tell you plainly. It won't attempt to interpolate or, fake the data just to keep the visualization running.
It's like an intellectual contract with the developer.
That's a great way to put it. The contract is, what you write is exactly what the machine executes, and the results are transparent. This principle is what drives the whole, often counterintuitive structure we're about to explore.
Okay, let's unpack this journey then, starting right at the foundation. The language. The sources tell us that Arooka began with a minimal, declarative, domain-specific language, a tiny DSL.
Yeah, and it was embedded directly into the SVG element using a custom attribute, data code.
Super simple stuff, like the example they give. Data code, circle 100, 140, tag 333. A command and its parameters.
That initial setup was, I think, brilliant because it established that direct text-to-output mapping and a very transparent interpreter. It was easy to read, easy to debug.
But they hit a wall.
They hit an architectural ceiling, and fast. The moment they wanted to add composition, say drawing a cluster of 5 circles and then rotating that whole cluster, the DSL became unwieldy.
And they were facing that classic fork in the road.
Yep. Do you expand the DSL syntax until it becomes this arbitrarily complex beast? Do you switch to a standard data format like JSON, which has its own overhead? Or do you try something radical?
And the radical choice, the crucial architectural pivot, was to adopt a Forth style, stack-based language. Now, for our audience, Forth is an ancient, minimal, but incredibly powerful language. It relies on reverse Polish notation, RPN, where operands precede operators.
So you'd write 3, 4 plus instead of 3 plus 4.
Exactly. And I have to ask, in a world dominated by JavaScript, Python, and JSON,
Yeah.
why choose Forth? Wasn't that an immediate barrier to entry, a source of, unnecessary complexity?
It sounds so counterintuitive, doesn't it? But Forth was chosen precisely because of the axioms. Complexity wasn't the enemy. Unaccountable complexity was.
Okay, unpack that.
Forth's stack-based nature and its dictionary structure provide this inherent extensibility, honesty, and inspectability better than almost any other language structure. In Forth, every single operation is a named word.
A function,
A
basically.
function, yeah. And every word either consumes values from the stack, produces new values onto the stack, or manipulates the stack. There are no hidden parameters, no unexpected side effects, and no implicit state outside of the stack itself.
So if the goal is truth without ornament, Forth delivers that because it forces the developer to declare the entire execution context explicitly.
Exactly that. When you run a word, you know precisely what the required inputs are because they must be sitting right there on the top of the stack. If they aren't, the machine stops and tells you.
Whereas with a complex DSL or even some JavaScript functions, you might have hidden state variables or complex parsing rules that obscure the actual data flow.
Right. Fourth is a transparent machine. Its state is always visible, right there on top of that single data stack.
That brings us straight to the core disciplinary measure of the language,
Mm-hmm.
stack discipline.
Yeah.
It's minimal, but it's also its greatest challenge.
It is the absolute bedrock. The interpreter has to rigidly manage that single stack. We see in the source code the core definitions immediately differentiating between literal values, like a string label, or the number 100 in executable words.
Which are the functions stored in the dictionary.
Right, so if the interpreter sees a number, it just pushes it onto the stack. Simple. If it sees a word, it looks up the definition in its dictionary and executes the associated code.
And the most basic primitives are designed purely for stack management. We see words like DUP,
Which duplicates the top item.
swaps the top two items.
And drop, which just removes the top item. Simple actions, but they're the building blocks for orchestrating much more complex functions later on. And this is where the system's guarantee of honesty really kicks in, fulfilling that truth without ornament promise. If a developer runs swap, but the stack only has one item on it.
It can't swap.
It can't. So the fourth machine throws an immediate disciplined error. Swap requires two items on stack. It doesn't crash silently. It doesn't return null or undefined. It halts and tells you precisely why it failed.
That instant feedback loop, enforced by the interpreter's rigid discipline, is key.
Yeah.
It prevents state corruption before it can even start.
Absolutely. The engineering goal here was what they called presence without performance failure. If something fails, we report the failure state plainly and immediately. You don't let it fester.
You mentioned the challenge of composability earlier, how that broke the simple DSL. How does Forth solve that?
It's solved by the ability to create user-defined words, or macros, using what are called colon definitions. You use a colon, comma, to start a new definition, and a semicolon boolean to end it.
So this is the engine of extensibility. It means that at runtime, the Arooka system is literally growing its own language. It's building its own dictionary.
Precisely. You can define incredibly complex operations as single, reusable words. For instance, you could define a word called red square that takes, say, a position and a size from the stack and draws a complex shape.
And that word, red square, becomes a first-class citizen in the dictionary, right alongside DUP or circle.
It does. This mechanism provides runtime dictionary growth, making the system truly elastic. It means a developer can inspect the entire physics engine, which is ultimately just a set of nested Forth words, at any time. It's all there in the dictionary.
Okay, so once they had the core JavaScript Forth machine working, the stack, the dictionary, the primitives, the next logical step was connecting it to the visualization layer, the SVG itself.
And that connection was deliberately direct. Graphics words like circle were defined to perform the final drawing step.
So they're the bridge to the DOM.
They are. A word like circle is defined to pop the necessary parameters x, y, radius, fill color directly from the stack, and then the underlying JavaScript uses document.createElementNS to emit that native SVG circle shape into the DOM.
So the code, let's say 100, 240, hashtag F100, circle executes. The interpreter pushes 100, then 200, then 40, then the string, hashtag F100 drew, then it hits circle.
And circle knows it needs 4 arguments. It pops hashtag F100 for the fill, 40 for the radius, 200 for y, and 100 for x. The stack is now empty, and a red circle appears at coordinates 100, 200.
That direct mapping is clean. It's honest. But as soon as the developers wanted to use repetition or build complex scene hierarchies, they needed transforms. And applying a global translation can pollute the state for everything else.
Right, you don't want to translate the whole canvas just to move one small part of your drawing.
And this leads to the first major structural extension in the architecture, an explicit transform system, built on maintaining a dedicated group stack.
This was their solution to avoiding global state pollution for transformations. And it's a really elegant one. Instead of modifying global SVG transform matrices, they introduced a layer of abstraction.
Managed by 2 new words, pushHG and pushOp.
Exactly. When you execute pushOp, the interpreter creates a new SVGG element, a grouping element, and immediately pushes a reference to that group onto this new separate Arooka group stack.
And all subsequent drawing commands are then appended as children of that new group.
Yes. And the transforms words like translate, rotate, or scale become specific commands that apply their effect only to the active group element that's on the top of that group stack.
So this is crucial. If you run 45 rotate, it only affects the current group.
Only the current group. Once you're finished drawing the components inside that rotated group, you run PPG. That pops the reference off the Arooka stack, and the drawing context reverts back to the parent group.
So it maintains transparency because the entire hierarchy of composition is explicitly defined by named words. You could literally trace it in the code and see the resulting nested G tags in the SVG DOM.
It's another layer of truth without ornament. The composition structure isn't hidden in some scene graph object. It's right there in the code you wrote.
Okay, that established a robust, extensible, and accountable 2D system. But the sources indicate that the visualizations they needed to build quickly demanded something more.
Much more than 2D.
The architectural demand for complex physical modeling forced the system to move from a fixed 2D plane to a generalized n-space. This is a huge conceptual leap.
It is. It's the transition from a simple drawing tool to a full-blown spatial modeling engine. The key insight they had was realizing that the logical coordinates of an entity, its true position in space, must be completely decoupled from its visualization on the screen.
So the particle's truth exists independent of how the browser decides to render it.
Precisely. The SVG is just a shadow on the cave wall. The real particle exists in this abstract n-dimensional space.
How is this n-space defined within the tight constraints of the fourth language? How do you even represent that?
They introduced a key system-level word, ndim. This word sets the active dimensionality for the entire environment. If you run 3ndim, the system knows it's working in XYZ.
And if you run 10ndim?
It's operating in a 10-dimensional space. And critically, this setting governs how many numbers subsequent dimension-aware words expect to find on the stack.
Ah, so it's a contract. If ndim is set to 4, then the next word that expects coordinates, say a word like particle, must consume 4 numbers from the stack.
It must. And if it only finds 3, the stack discipline immediately halts the execution with an error. It's that honesty principle again.
So the particle word is the core entity constructor.
Right. It consumes ndim number of values from the stack and creates the core entity, an n-dimensional particle object. Internally in the JavaScript, this is just a simple array holding the particle's true coordinates. But that separation is key. The particle object is the ground truth, and the SVG is simply a momentary projection of that truth.
To make this system workable, though, they had to establish a baseline relationship between this abstract n-space and the fixed 2D SVG canvas. We see the definition of a logical coordinate system established using the word set origin scale.
That word is critical. It maps the abstract origin, where x0, y0 is in their logical universe, and a scale factor onto the SVG's pixel-based drawing space.
But there's a crucial non-negotiable piece of logic here. The SVG standard defines the y-axis as increasing downwards.
Whereas standard scientific and mathematical notation, what you learn in school, defines y as increasing upwards. They're inverted.
So they had to introduce an explicit inversion into the system.
Absolutely.
Yeah.
The logical TOTCG utility function is where this is handled. You can see the formula in the source. SI equals nv.origin yyNV.scale. The subtraction handles the flip.
And this is a necessary piece of non-ornamented logic. It's not hidden.
It's totally transparent. It ensures the system doesn't lie about how it translates coordinate systems. The inversion is baked right into the environment variables, not hidden inside some complex magical drawing function.
Okay, now we get to the critical, and I imagine very complex, bridge, the project word. If the system is operating in 4D, 5D, or 10D, how does the system, constrained by a 2D display, make sense of that data for drawing? This is where the visualization compromise has to happen.
Projects is the core translation engine. It's its job to consume an n-space particle object from the stack and produce the 2D logical coordinates x and y required for drawing.
So if the ndim environment variable is 2, it's trivial. It just passes the x and y through.
Trivial pass-through, but the architectural challenge comes with higher dimensions, of course.
And the sources show they implemented a very simple, predictable projection mechanism. They specifically avoided complex, resource-heavy calculations like a full perspective projection matrix.
They chose simplicity over realistic simulation. For 3D, it uses a simple depth queue. It just adjusts the x and y coordinates based on the z value with a formula like x plus equals 0.3, y plus equals z 0.3.
This decision feels like a direct reflection of that truth without ornament philosophy.
It is. They call this implementation grace without algorithms.
I see. If they had introduced a full perspective matrix calculation, that algorithm would become a black box. It's complex math, there's hidden state, it's difficult to debug or verify.
Exactly. By choosing the simple additive depth queue, they keep the projection math totally transparent and inspectable. It's honest about the simplification.
It's saying, we are acknowledging the third dimension,
Yep.
and here is our simple, explicit rule for displaying it.
Right. The user knows exactly what visual distortion they are seeing and why. It prevents any complex hidden logic from corrupting the core truth of the particle's n-dimensional coordinates.
This sounds like a system prioritizing safety and consistency above all else. Which brings us back to stack discipline and what they call the graceful fallback principle.
Yes.
What happens if the project word receives bad input? Say a text string instead of a particle object, or maybe a particle that somehow holds 5 coordinates when ndim is set to 3.
If the projection routine detects an inconsistent state like that, it triggers the graceful fallback. The system logs a descriptive warning to the console, for instance. Warning, particle type mismatch, skipping projection.
Well, and
Crucially, project then pushes nothing back onto the stack. It just stops.
And because project pushes nothing, the subsequent drawing words like circle will immediately fail because they're expecting x, y, radius, and fill on the stack, and none of those are there.
Correct. The system guarantees that if it can't produce an honest 2D coordinate pair, it will not lie or fake the data. By pushing nothing, it forces the entire rendering chain for that one entity to gracefully skip, ensuring the next operation starts with a clean slate. It prevents a cascading error that could potentially pollute the stack for entirely unrelated particles later on.
The integrity of the stack is paramount.
Always.
The sources detail the challenge of achieving stability during this transition. They mentioned that early complex user-defined words, like a hypothetical circle dotty, broke constantly because of mismatched stack inputs and these newly introduced particle objects.
This is a classic fourth-style debugging phase. The stack signatures, the order and type of data words expect, they become complex very quickly. If particle consumed 3 items and circle expected 4 items, and your user-defined word didn't perfectly align those outputs,
It's instantly unusable.
instantly, the solution was to establish a clean, minimal, stable base, which they designated in the sources as VRO.
Meaning they created specialized words that completely encapsulated the entire process to ensure that the internal stack machinations of, say, projection never leaked out to confuse other drawing definitions.
That's right. The word particle.e is the perfect example they give. It handles the entire chain of accountability. It takes raw n-space coordinates from the stack, runs particle to create the object, runs project to get the 2D coordinates, and then runs circle with the appropriate radius and fill. It guarantees the 4 parameters needed by circle are perfectly arranged, regardless of the input dimension.
And I noticed they introduced another dedicated drawing word, projected circle. Why the need for a separate drawing primitive? It seems redundant at first glance.
It was necessary to avoid a nasty double transformation error. The logical coordinates, the x and y that come out of project, have already accounted for the scale and the y-axis inversion.
Ah, I see. They represent where the shape should be in SVG space, not logical space.
Exactly. If they had used the standard circle word, which was built to handle logical coordinates, they would have risked applying that scale and origin mapping twice. The shape would appear in the wrong place.
So projected circle was a word that accepted the raw SVG coordinates, CX and CY, directly from the projection stack.
Yes, it was about ensuring the foundation was absolutely trustworthy before they started simulating dynamics on top of it.
This stable n-dimensional foundation, built on these explicit, accountable words, now sets the stage for the next dramatic leap, simulating dynamics and force. The sources note that when most systems move into complex visualizations, they immediately implement a continuous animation loop.
A tick function.
Yeah, a tick function running at 60 frames per second, calculating distance traveled over delta time, or dt. But Arooka explicitly rejects this time-based model.
This is a massive philosophical break from traditional game engines or visualization frameworks. They rejected the continuous time model tick, DT, request animation frame, in favor of a pure vector transformation model.
And the core principle being enforced is,
Nothing evolves automatically or continuously.
so motion is not something that just happens over time. It is discrete. It only occurs when an explicit, named fourth word is executed by the interpreter.
Exactly. Every single change to the system state is an explicit transaction. If you want to move a particle, you have to execute a word like 104 self which applies a vector addition of 1, 0, 0 to its coordinate.
And if you want to spin it?
You execute 0, 1, 4, 5 ROT self, which applies a rotation. Everything is deterministic, explicit, and accountable. You know precisely when and why the particle changed state, because you can point to the single function call that caused that change.
What was the architectural reason for avoiding the continuous time loop? Was it just about performance, or was it something more fundamental?
It was fundamental. It was about determinism and inspectability. A continuous time loop introduces subtle non-determinism, especially in a browser environment where frame rates can vary. It makes debugging causal chains incredibly difficult.
Right. Was this bug caused by the physics update or the rendering update? It gets blurry.
It does. By enforcing discrete transformations, the builders guarantee that the entire history of the universe, the path of every single particle, could be precisely reconstructed by logging the sequence of fourth words that were executed. If a particle moved, it's because an explicit word was called. There's no hidden influence from a variable dt.
To support this pure transformation model, the particle essence, the data object itself, had to become much richer than just an array of coordinates.
Absolutely. The definition expanded far beyond that simple n-dimensional coordinate array. It became a container for the full n-dimensional state and a lot of crucial metadata.
Like what?
Like a unique id, the current chords array, arbitrary tags for classification, and metafields for other properties like color or size. These fields, especially the coordinates, are preserved as the ground truth, and the 2D SVG is merely the projected, momentary view of that truth.
And for this robust n-space transformation model to work, they couldn't just have simple numbers and strings on the stack anymore. That wouldn't be powerful enough for vector math.
Correct. This forced a fundamental upgrade to the internal design of the fourth stack itself. It had to become object-aware. This led to the introduction of first-class n-dimensional algebra as distinct stack types.
How does the interpreter manage this internally? How does it distinguish between a scalar number 100 and a vector literal like 100 fists?
It requires a more sophisticated internal JavaScript structure for the stack items. Previously, a number was just a primitive value. Now, every single item on the stack is effectively a complex JS object wrapper.
A wrapper that contains what?
It contains at least three things. A type tag like scalar, vector, string, or quaternion. Then the value itself. And optionally, some dimension metadata. So when the interpreter's tokenizer sees 100 in the code, it sees the brackets, creates an object tagged type vector, and pushes that single structured object onto the stack, not three separate numbers.
It's like upgrading the stack from a simple calculator display to a scientific graphing computer. It can hold complex entities that have their own internal mathematical rules.
That's a perfect analogy. And this is absolutely necessary for robust force application where you need to perform vector addition or subtraction, regardless of whether your ndim is 3 or 5 or 50.
And that necessity became even more acute when they started dealing with rotation. Standard 3D rotation using, say, rotation matrices or Euler angles introduces all sorts of problems.
Oh yeah, gimbal lock, for one. And they're really hard to generalize cleanly into n-space.
So the solution they landed on was the introduction of quaternions.
Yes. Quaternions are, they're notorious for being mathematically complex, but they are essential for stable, complex rotations. So they were introduced as another distinct first-class stack type.
Because they needed rotation to be as deterministic and explicit as translation was.
Exactly. Quaternions offer a much cleaner, singularity-free algebra for rotations in 3D and can be generalized to n-space. They become constructible via specialized words like xis angle, which would consume an axis vector and an angle from the stack and produce a single quaternion object back onto the stack.
And the core rotational mechanism is then embodied in the word ROTV, rotate vector.
ROTV is the workhorse. It's defined to consume a quaternion object and a vector object from the stack, perform the complex quaternion multiplication, and then push the resulting rotated vector back onto the stack.
So this provides the clean foundation for defining all high-level rotational forces, like spin or twist or orbital mechanics. The complexity is abstracted away into the mathematical object itself, not hidden in global state variables. Now we arrive at the architectural challenge of scale and access control. If you have many entities interacting, a sun, a main particle, and an environment, how do you prevent the sun's definition of, say, emit force from accidentally polluting the main particle's ability to define a Pli force? This demands scope control.
And this leads to what I think is one of the most beautiful solutions in the whole system, the multi-interpreter architecture.
So not just one big fourth machine.
No. Instead of one global fourth execution environment, the Arooka system was structured to use three fully separate either-fourth interpreters,
Three separate interpreters.
each with its own completely independent stack, its own dictionary, and its own execution context. They named them the environment, env, the sun, emitter, and the main receiver.
Why three, specifically? What are the clearly defined roles here?
The separation defines the universe's mechanics and enforces the rules. First, you have the environment interpreter. It handles global state, the logical coordinate system, projection definitions, and critically managing the array of propagating force objects. It's the physics sandbox manager.
The stage.
The stage, exactly. Second is the sun emitter interpreter. Its dictionary only contains words related to energy creation, force composition, and emission. It cannot access the main particle's internal coordinates directly. It can only emit forces into the environment.
And the third?
The main receiver interpreter. Its dictionary is focused on self-transformation, reading sensor data, calculating trajectories, and applying received forces. It only ever transforms its own particle object. It can't affect the sun or the environment directly.
So this separation enforces strict accountability. The word emit force only exists in the sun's dictionary.
Right, so only the recognized source of energy can create forces, and the main particle only has access to receive force and apply force.
This architectural boundary prevents dictionary pollution and unauthorized access. If the sun tried to directly modify the main particle's coordinates,
the word wouldn't exist in its dictionary, or it wouldn't have the necessary access privileges to the main particle stack. Every single interaction must go through the environment as an intermediary.
which is the mechanism of the wave packets.
Exactly.
This sets us up perfectly for the pinnacle of the architecture: force transmission via wave packets. Because they rejected that continuous animation loop, they had to invent a discrete, explicit mechanism for energy and force transfer across these independent interpreters.
The first step in that chain was to define what a force is. And they established that a force is not a single push-pull vector, it's a structured stack object, a miniature, complex data packet containing multiple distinct sub-effects.
A design that models the complex nature of light and energy interaction, which is rarely singular.
Right, it's not just a single number representing push.
The force constructor word requires 5 distinct components to be on the stack. This is fascinating. Can you break down what those 5 effects represent conceptually?
Absolutely. And the design reflects an attempt to build a physics-agnostic engine that can model interactions far more complex than simple Newtonian push-pull. The first component is thermal.
Heat.
Heat. This handles heat flow and can be represented as a vector for, say, directional heat from a thruster, or just a scalar for an ambient temperature change.
Okay, what's next?
Second is electromagnetic. This is for things like polarization, field orientation, or other complex field interactions. It's often represented by that new quaternion type or direction vector.
Number 3.
Photon gravity. This is a specific vector component dedicated to effects that model space-time curvature or gravitational interaction. They kept that distinct from simple translational force.
So it's a specific kind of toll.
A very specific kind. Fourth is illumination, which is a simple scalar component representing radiance or brightness. This primarily affects the particle's visualization metadata, its color rather than its position.
And the 5th one sounds a little different. Thermin.
Therm is a distinct, complex force component, and it's introduced via its own dedicated Thermin word. This component is designed to apply a configurable action. It could be vector addition, scaling, or rotation, and it acts as a kind of catch-all for complex, custom physics effects that need their own dedicated handling.
So the sun interpreter executes a sequence of operations, placing these 5 distinct objects onto its stack, and then it runs the force word.
And the result is a single, composite structured object that sits on the sun's stack, ready for transmission.
Okay, so the force is built. How is it sent?
The process of explicit transmission begins. The sun interpreter executes the word emit force. This word consumes that complex force object from its stack and creates a discrete force wave packet entity inside the environment's global state.
Specifically into the nv.force waves array.
That's the one. And this wave packet is a real, measurable entity in the universe. It stores its full payload, all 5 components, plus its originating coordinates, which is the sun's current position, and its direction vector.
It honors the principle that forces must be physically emitted into the world. It's not a remote procedure call.
It's a particle of energy. Now, since there is no tick function, these waves don't just travel magically through space. Their motion must also be explicit.
So the environment interpreter has to do something.
The environment interpreter must execute the word propagate forces. This is the critical maintenance function for the universe.
And propagate forces explicitly iterates through all the existing wave packets in that ne.forceWaves array.
And it moves them along their internal direction vectors by a specified step size, which is a number passed on the stack.
So if the environment runs 3 propagate forces,
Every single wave packet in the universe moves exactly 3 units forward in its defined direction. This maintains the no-tick principle. It ensures vector motion is deterministic, explicit, and accountable. It only moves when told to by a named word in the environment's dictionary.
okay, so the force is emitted, it's propagating. Finally, it must be felt. The main particle, which has its own independent execution loop, runs the word receive force.
And this word is its sensor. It searches the environment's wave array for a packet that is spatially near the main particle.
And that proximity check is usually within a defined small radius, say 0.5 units. The force must actually be close enough to matter.
No action at a distance.
And if a packet is found within that radius,
The crucial step happens. The packet is consumed, it's physically removed from the environment's force waves array, and its multi-component payload, the 5 sub-effects, is pushed onto the main particle's stack.
and the cycle completes when the main particle executes a pi force.
Apply by force pops that structured force object, unpacks the 5 components, and explicitly applies each sub-effect as a transformation vector addition, scaling, or rotation to the main particle's own n-dimensional coordinates.
It's a closed 4-part loop: emission, propagation, reception, and application.
That 4-step process is the full definition of interaction in the Arooka universe. It is a stunning example of how to build complex, interacting physics using only discrete, explicit, and accountable language transformations rather than a continuous simulation. The 4th machine makes every action a recorded, auditable event.
This is a truly remarkable achievement in foundational systems design. We have tracked this system from a simple single-line SVG declaration all the way to a complex, forth-driven, n-dimensional vector space featuring 3 independent interpreters and a physics-agnostic wave packet transmission system.
It really is, as you said earlier, an operating system for a tiny, deterministic universe.
What stands out most profoundly for me is the relationship they establish between language and physics. By choosing forth, and by defining every interaction force, rotation, movement as an explicit named word in the dictionary, the builders guaranteed that their universe was completely deterministic.
All change is traceable, it's accountable, and it's inspectable just by observing the sequence of executed words. There's no mystery.
That structural integrity is the key takeaway here, I think. The project successfully created a world where motion and force are not continuous processes integrated over time, but rather discrete, explicit transformations applied by a function call and named word.
And this deterministic setup raises an absolutely crucial question for anyone building complex systems, whether they are physical or computational. In a world built entirely on explicit stack-driven words, where every action is a named, finite transformation, is there any possibility left for true emergent behavior? Or is everything perfectly predictable from the start?
That's a great question. And think about the implications of the wave packet design itself. What happens when a multi-component force, fully defined and executed in the sun's dictionary, is emitted into the environment?
It becomes a physical entity with direction and speed.
But what if no particle ever executes receive force? What if it misses everything?
Then that force packet continues to exist. It keeps propagating indefinitely. Every time the environment runs propagate forces, it's a ghost in the machine.
In a deterministic world like Arooka, the unapplied potential of that force packet simply continues to exist, defining the architecture of a universe built on potential energy that is never converted. It becomes a permanent, measurable, yet unused structure, waiting for a receiver that may never, ever arrive.
And that's something worth exploring in your own systems.
Yeah.
What's the cost of unreceived messages? What happens to potential that's never actualized? It's a fascinating thought.